In this video, we're going to check out another special right triangle. So we already looked at 45, 45, 90s, and in this one, we're going to start with an equilateral triangle. And you can see in the diagram, that's what I've got below. So I've got equilateral triangle ABC. We've talked throughout the year about properties of isosceles and equilateral triangles. And in this particular one, what we're going to do here is we're going to look at what happens when I drop an altitude straight down here. So I'm going to drop an altitude straight down, and just to kind of jog your memory, we know that an altitude is really just the height of a triangle. So it goes from a vertex of the triangle, extends through the opposite side at a 90-degree angle. It's perpendicular to the opposite side. So here's the situation that I had. I started with an equilateral triangle, and we're going to drop an altitude down, and what that does is split this equilateral triangle into two congruent triangles. So throughout the year, we've looked at what happens when we do that with an isosceles triangle, but also an equilateral. So this is an altitude, but we know and we've proven that if you have an altitude of an equilateral, then it is also the perpendicular bisector. So an altitude is also a perpendicular bisector, which means it's perpendicular, which is part of the definition of an altitude, but it also splits that opposite side in half. So this side BC now gets split into two congruent sides, and we'll call this point D here. So BD is congruent to DC. We also know that an altitude is an angle bisector. Anytime you drop an altitude for an equilateral or for the vertex angle of an isosceles, it's going to be an angle bisector. So up here, this is the angle that it's going to chop in half, so these two angles are going to be congruent. And there are a lot of other properties. It's also the median and a couple of other things. We're going to focus on the fact that this is a perpendicular bisector, and also that it's an angle bisector. So we know that an equilateral triangle, if it's got congruent sides, it also means that it's got congruent angles in here. So I can come in here and I can label these angles. I know that, again, from the triangle sum, we've got a total of 180 degrees, but equilateral means equiangular, and I've got three angles, so if we chop that by 3, that'll give us the angle measure of each one of these angles, and we've looked at that before this year. So I know that this is going to be 60, this is going to be 60, and because this altitude is also an angle bisector, this whole angle would be 60, but I've chopped it in half, and so this is now going to be 30 degrees, and this is going to be 30 degrees. So what we've created basically is from an equilateral triangle, we've created these two 30, 60, 90 triangles. 30, 60, 90 triangles. And these triangles happen to have particular characteristics that we're going to go through and show always work here in a second. Alright, so here's the scenario. We're given a 30, 60, 90 right triangle. And again, we created that out of an equilateral triangle. You can see that using the dotted lines. But what we want to show is that we can actually find an expression for the measures of each side, similar to the way that we did it with the 45, 45, 90 triangle, or the isosceles right triangle. Alright, so given a 30, 60, 90 right triangle, so we're going to start this off by just saying, given the diagram, I've got everything labeled here in the diagram. So given that diagram, what we're going to do is use the fact that we know that this was an equilateral triangle. So here's what we're going to do. We're going to start with, we labeled this point D here. We're going to start by labeling this point X. So let BD have a length of X. Well, we know that because this is an altitude of an equilateral, it's also the angle bisector, and it's also the perpendicular bisector. So essentially, we know that BD is going to be congruent to DC, and if we double that, we know that BC is going to be congruent to AB and AC. In other words, all of these whole side lengths of this equilateral triangle are going to be congruent. So if you chop it in half, and this is X, then AB is going to be 2X. All right. So because of that fact, we can go through and we can figure out, hey, what's AD? What is the length of AD? And this, we're going to revert back to the fact that this is a right triangle. So let's go ahead and write our statement. If BD is X, then AB is equal to 2X. And that has to do with the fact that it's an equilateral triangle. So the next thing is we want to look at Pythagorean theorem. And Pythagorean theorem tells us that we've got our hypotenuse squared is going to be equal to BD squared, or X squared, times whatever AD is. I'm sorry, plus whatever AD is squared. So this is the thing that we're trying to figure out. So what we can do is we can go through. 2x squared is going to be 4x squared when we apply that exponent. And we're going to subtract our x squared from the right side. And that's going to be equal to AD squared. Now we want AD by itself. We can also simplify this left side. When we simplify it, we get 3x squared. That's equal to AD squared. And take the square root, and what we're left with is that altitude, aka perpendicular bisector, aka angle bisector of this particular thing, is always going to be whatever this side is, BD, times root 3 when we simplify. Okay? So here's the key. We just showed that this works, x root 3. All right, there's a little bit of a pattern here. Here's the pattern. It is 1. The ratio of these sides is going to be 1 to 2 to root 3. All right, and the key is that we define this based on the side opposite that 30-degree angle. So this is BD is always going to be the shortest side because it's opposite the shortest angle. And we got to make sure that when we go through these problems that we define it based on that. So whatever my shortest side is, I can double that shortest side and get the hypotenuse. And I can take that shortest side and multiply it by root 3, and that would give me this side here, the other side, other than the hypotenuse. All right, so let's look at a couple applications of this. Here, again, we're always defining our sides based on the shortest side, and you've got to be careful of this. So here's our 30-degree angle. The side that's opposite that 30-degree angle is going to be the smallest, and in this case, this is our x. Okay? So if I want to find the other two, I know that they're written in the ratio of 1 to 2 to root 3, or in other words, x to 2x to x root 3. Okay? So x is always determined or defined as the shortest side. So I take this measure, and if I want to find RQ, I know that RQ is going to be whatever x root 3 is. So RQ is equal to x root 3, and in this case, x is 7. So 7 root 3. Sorry, a little typo there. RQ is going to be equal to 7 root 3. If I want to find the hypotenuse, I simply, and the hypotenuse in this particular case is PQ, but if I want to find that, and I already know what the shortest side is, the length of the shortest side is, I just take 7 and I double it, and I can get my hypotenuse. All right, so this side down here is going to be 7 root 3, and this side here is going to be double the length of the shortest side, or in other words, 14 for this particular case. A little bit tougher one is when you're not given the shortest side, so we need to kind of use what we know and revert back to finding the shortest side. Remember, this is always x still. The shortest side is how we define the relationship between these other two. So RQ, we know that in terms of the shortest side, x, RQ is going to be equal to x times root 3. So in other words, RQ is 12, so 12 equals x root 3. Solve for x, and you'll get your shortest side here. So I'm solving for x. I'm going to divide by root 3. Just like in the last video, if we get a root in the denominator, we need to make sure that we rationalize. So let's go ahead and rationalize this. 12 divided by root 3, and we're going to multiply that by root 3 over root 3 in order to rationalize it. That's going to give me 3 in the denominator, 12 root 3 in the numerator. Simplify and you end up with x equals 4 root 3. So we've now taken this side and used that relationship in order to find our shortest side. All right, so the last thing left to do is use this shortest side in order to find the hypotenuse. And when I find the hypotenuse, I'm just taking the shortest side. I know PQ is going to be equal to double whatever the shortest side is. And in this particular case, the shortest side is 4 root 3. So PQ, the hypotenuse, is going to be 8 root 3.